Today we're going to be able to understand how to represent and analyze data in a scatter plot. By the time you walk out of the door today, you should be able to organize data to see patterns more clearly. And our 8 mathematical practice that we'll be focusing on is looking for and making use of structure with our data. We're going to see data presented to us in forms of tables and in forms of scatter plots. And we will formalize that definition of a scatter plot today. Let's go ahead and open up your workbooks, please, to page 2. And go ahead and pause the video at this time and jot down anything you notice or wonder about this set of data, where the input data or the X data is length of short side in centimeters being compared with the length of the perimeter in centimeters of triangles. So some things that I noticed when analyzing this data, or kind of digging in a little deeper with the data, was that it appeared to me that as the perimeter increases, or the perimeter increases when the short side length increases. So perimeter increases when short side length increases. I also noticed that the perimeters may be rounded possibly to the nearest half unit. And another thing I really noticed was that the data is not necessarily in any obvious order to me. It kind of seems all over the place. Which takes me to my, one of my wonders was, is there a pattern to the data? Based on the way this data is organized, that's really hard for me to see, and I was wondering that. Is there a pattern at all to this data? I also wondered, are the measurements exact, or are those rounded measurements? So like that 0.25 or the perimeter when it was 7.5 or 9.5, are they rounded to the nearest half, or are those exact? So are measurements exact? And then my last wonder was just kind of why these triangles? Or is there any specific reason why these measurements were chosen, or are they just kind of random measurements? So if you don't have any of these notice or wonders and you'd like to add them to your notes right now, at the bottom of page 2, please do so. If any of them stand out that I jotted down that you'd like to add, go ahead and pause the video and take a moment to do so. Before beginning our next activity on page 3, let's go over a little bit of background information on isosceles right triangles that I think will help you be a little bit more successful with this activity. These questions are not in your book, so if you could please just stop and think about them now. If you want to jot them down with a dry erase marker on the desk and press pause and check your responses with mine, feel free. But just a couple recaps about isosceles right triangles, so that way the next data activity will make a little more sense possibly. So what does it mean to be an isosceles triangle? Just a reminder that an isosceles triangle means that 2 of the 3 side lengths are the same, right, or equal. Okay, so I can show that if I want to in this diagram by writing down those tick marks to indicate they're the same side lengths. What does it mean to be a right triangle? Okay, that obviously means there is a right angle present in the triangle, right? So there is a right angle, and that is notated, we know, with that little box in the corner. How do we measure the perimeter of a triangle? Reminder that to measure the perimeter of any figure, it's just adding up all the sides. So in this specific figure, perimeter is by adding up all three sides would give us the perimeter. And should there be a relationship between the length of the two short sides and their perimeter? So that question might be kind of tough to answer right now. So after going through the data and analyzing the data from the next activity, we might be able to better answer that. So if you want to make a hypothesis or educated guess about that last question, maybe we can hopefully come to a conclusion on that after our next activity. All right, so you've got a set of data on page 3. It says, here's the table of isosceles right triangle measurements from the warm-up and an empty table. This is the same data from the warm-up, so we're going to go ahead and utilize this data to answer the next set of questions at the bottom of page 3, which continue on to the top of page 4. So at this time, go ahead and pause and answer these questions, questions 1 and 2, to the best of your ability, and then you can go ahead and check your work with mine. So the first question asks, how can you organize the measurements of the first table so that any patterns are easier to see? Write your new organized measurements in the empty table. So this could vary. Your table setup does not have to be the same as mine, as long as you found some sort of a way to organize your data that maybe makes a little more sense. I was thinking when I reorganized the data was that I was going to order it from the length of the shortest side, from shortest to longest. So I noticed that the first entry is in fact the shortest of the shortest sides, and the perimeter is 1. I then noticed 2 is not the next shortest. The next shortest is 0.5, and that triangle has a perimeter of 2 centimeters. The next shortest, or longest after that, would be a side length of 1 centimeter with a perimeter of 2.5 centimeters. The next one I found was 1.25 centimeters with a perimeter of 3.5, and then 1.5 with a perimeter of 5, and then 2 centimeters with a perimeter of 7.5, and then 3 centimeters with a perimeter of 9.5, and then I found 3.5 to be the next largest with a perimeter of 12.5, and then 4 centimeters with a perimeter of 14, and then finally the next or the longest of the side lengths was 6.5 or 6.5 with a perimeter of 22. So that's just one way to reorganize the data by the length of shortest sides. You could have done it in reverse, I suppose, and went from longest to shortest, and then your data would be completely reversed. But if you didn't come up with a strategy on how to reorganize the data, please go ahead and copy mine down now, and then we can answer possibly questions 2A through C a lot easier, hopefully. So question 2 asks, for each of the following lengths, estimate the perimeter of an isosceles right triangle whose short sides have that length. Explain your reasoning for each triangle. Okay, so 2A asks about a length of a short side that is 0.75 centimeters long. Well, I know that 0.75 is going to fall in between 0.5 and 1. So therefore, its perimeter should fall in between 2 and 2.5, right? So what is a number between 2 and 2.5? How about 2.25? So for A, I can estimate the perimeter to be about 2.25 centimeters. And again, that's just picking two numbers that it falls in between for my mathematical reasoning. It's between the perimeters of the triangles whose short side lengths were 0.5 centimeters and 1 centimeter. So 2.25 centimeters falls between the two perimeters that correspond, which would be between 2 and 2.5. All right, then how about for the length of the short side, who is 5 centimeters? So if I go back to my table, 5 centimeters is going to fall somewhere between 4 and 6.5, which tells me my perimeter should fall somewhere between 14 and 22. So maybe a good estimate for that one would be around 17 centimeters, falls somewhere between 14 and 22. So I'm going to estimate the perimeter for this one to be approximately 17 centimeters. And again, it's a little less than halfway between 14 centimeters and 22 centimeters, so that's my reasoning here. About halfway between 14 and 22 centimeters. All right, then finally, C, which you should be answering on page 4. B and C are on 4. The length of the shortest sides is 10 centimeters. So if I go back to the table of values, I know 10 centimeters is going to come somewhere after 6.5. So therefore, I know the perimeter has to be larger than 22. So how can I start to think about what would be a logical perimeter? I may want to dive a little deeper into the numbers. And if I look at, for example, like 1, a side length of 1 has a perimeter of about 2.5. So maybe I want to round that to 3. So if I'm going to round that to 3, then that means if I go to a side length of 3, and I think about that as being 3 times the size, 3 times 3, oh yeah, that's close to 9, right? 9.5. So I can kind of use that reasoning and think about it that way. And if I'm going to think that a short side length of 1 centimeter has a perimeter close to 3, then a short side length of 10 centimeters should have a perimeter close to 30, because 10 times 3 will get me to 30, right? Remember, these are just approximations. So that's how I can approximate that the perimeter might be approximately 30 centimeters. And again, my reasoning for that is as the short side goes up by 1, the perimeters goes up by approximately 3. Okay, again, that's an estimate, a rough approximation, so I was able to take that 10, multiply it by 3 to get that approximately 30 centimeters. All right, so at this time, if your approximations are close to mine, again, they don't have to be exact, then you're good to go and your reasoning makes sense, but if you need to adjust your notes, please feel free to do so on pages 3 and 4 at this time. We're going to go ahead and skip the Are You Ready for More, but if time remains at the end of class when you're done with your cool down, I'm going to ask that you come back and attempt it and see how it goes on your own. We're going to go ahead now and take a look at this activity synthesis. Unfortunately, this scatter plot is not in your workbook, so I need you to take a look at the scatter plot here, and hopefully it will help you answer some of these synthesis questions. It says, what patterns do you see in the data when it is graphed? So if I look at this data, I see that the x-axis is labeled length of short sides. I see that the y-axis or the vertical axis is labeled perimeter. And seeing the data graphed in a scatter plot for me, I can see that the data is very linear-like. It is not perfectly linear, but it looks like a line, right? So I can say it's close to being linear, but it's definitely not perfectly linear, but it has that linear-like look to it. How could you use the graph to estimate the perimeter for the isosceles right triangles with short sides of 0.75 centimeters, 5 centimeters, or 10 centimeters? At this time, go ahead and pause the video and see if you can answer these 3 questions. Write your numbers, your corresponding perimeters down, and you can either do this where there's some space in your workbook or write on your desk with a dry erase marker and check them with me. So if I'm looking at 0.75 centimeters for the shortest side length, that corresponds to the x-axis. I'm going to find where 0.75 approximately falls on x and go up, 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 until I reach where a possible point might exist, which is around 2. So any close perimeter of 2, maybe 2.1, somewhere in that region is a reasonable estimation if the side length was 0.75 centimeters. Now how about a side length of 5 centimeters? So I'm going to use that same mathematical reasoning, and I'm going to go to 5, and I'm going to go up, 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 where I think the data might fall, and I might get a point right around there, and I'm going to go across, and I'm going to see, oh, well, that's somewhere between 14 and 16. So maybe a logical estimation for the perimeter would be around 15 centimeters if my side length were 5. All right, then finally, I'm going to go ahead and take a look at if I had a side length of 10. Now 10 is way off the graph. I don't even see that on the x-axis. So I know if it's beyond the x-axis, it's going to be, the perimeter is going to be beyond the y as well, so it's going to be higher than 24. So here's where that whole reasoning comes into play from earlier. If I look at my numbers here, how did I get from 5 to 15? Well, if I multiply it by 3, that would work, right? So if I use that same approach, 10 times 3, I get a perimeter of approximately 30 centimeters. So that falls in line with what we estimated with the tables. Now we can see what that estimation could look like using a scatter plot instead. So hopefully your estimations, again, were close to mine with 2, 15, and 30. All right. We will more formalize our definition of a scatter plot at the end of our lesson today, so you can get that in your notes. But you do have an example of 4 scatter plots on page 5 in your workbook. Your next task here is to take these 4 scatter plots and match them to the 4 tables that you have on the handout that you grabbed when you walked in the door. Just to clarify some terminology from these tables, if you see fuel efficiency in miles per gallon, that refers to how much fuel, how efficient the fuel is being utilized. If you see kilowatts per hours, that is a term that the electrical energy that most electrical companies use to measure how much electricity a customer used to determine how much to charge them. And then another term that you might be unaware of on the backside is the term carat. We are not referring to carrots that you eat, but rather we are talking about the weight of diamonds. So you may have heard I have a 1 carat diamond or a 2 carat diamond. So that refers to the weight of the diamond. Or other precious stones are used to be weighed in carats. All right, so now that we clarified some of the terminology, you're going to go ahead and you're going to pause the video, and your tasks, though, prior to pausing, are to do 3 things using these tables on page 5. You're going to determine which graph matches which table of values, and you're going to give each graph or scatter plot on page 5 a title, similarly to the title given to you on top of the table. And then you're going to go ahead and label the X and Y axes, or the horizontal and the vertical axes, to align with the data presented in each table. Once you are done assigning an overall title to your graph, labels for the X and Y axes, go ahead and press play and check your work with mine. All right, so for the first graph on your page in the upper left-hand corner, I have this one matching with the 20 used cars table. So this one would be 20 used cars. So hopefully you found this data to match that. One way to check to see that it matches is to try to find some points on the graph that match the points in the table, right? So when doing so, first we may want to figure out what's X and Y here. So if I'm looking at the x-axis, the way they have it labeled is starting from 0, then they're counting by 30,000s. So which data seems more reasonable to count by 30,000s if I'm going all the way up to 150? Is that the price? Is there a car priced almost as high as 150,000, or is that the mileage? So if I look closer at the data, the price of the car, the highest price I'm seeing is, looks like 20,000, just over 20,000, 20,998, right? So that would make more sense for the price in dollars to be my y-axis here, because that goes up to 21,000, which is just above that 20,999. So therefore, the mileage should be the X data here labeled on this first graph. And again, we can, like I said, we can further check that by picking any or several data points to see, do they line up on this graph? So I'm going to go ahead and take a look at, let's pick one in the middle. The 18,998 for the price and the 47,000 for the miles. So I'm going to go over approximately 47,000. Which would put me right around here. And if I go up, I should be at just under 19,000, which here we are. Up. There's that point represented. So, and again, you can do that. You can test several more points if you're unsure that you picked the right, graph scatter plot to go with this correct data from the tables. All right, for the next scatter plot, this one I have labeled 30 days in August, like their table. Okay, this time around when I analyze the X and Y axes and try to figure out what makes more sense to go with which set of data, I'm looking at the x-axis and their data ranges from 72 to 102. So if I'm looking at the data in the table, to me, that makes sense to be the degrees Fahrenheit, right? Because I see a low, the lowest is around 70, where is it, 76, and the highest is 100, it appears. So to me, this makes sense to label it daily high, and that's in degrees Fahrenheit, right? So with that said, then the y-axis should be labeled energy consumed in kilowatt hours. And again, that's kilowatt hours. Kilowatts. Sorry, I ran off the room there in my box. All right, so now, and again, you can always check that by testing a few of the points, right? My next scatter plot here, I have this one labeled as 20 diamonds. So this one I have as 20 diamonds. Okay, so then when I went and dug a little deeper to figure out what should I label X, what should I label Y, if I look at how they set up the x-axis and their scaling, they went from 0.9 to 2.1. That data ranges with the weights in carats. So I label the x-axis weight, and I should put that in parentheses, our units of measurement is carats, right? And then, oh, that's 1R, not 2, sorry. Then after that, that would mean my y-axis should be labeled price in dollars. All right, and then finally, that fourth scatter plot would make the most sense then to be titled my 20 new cars. That's the last set of data we haven't used yet. 20 new cars. And when further analyzing the X and Y axes here for the 20 new cars, if I look at the table, it looks and it appears that the X-axis ranges from 1,000 to 2,500. And which data better fits that? Well, that would be our mass in kilograms, right? So therefore, my Y data should be fuel efficiency in miles per gallon. All right, so hopefully you recognize that these four tables match these four scatter plots in this order. If you need to adjust anything, if you have anything mislabeled or you need to add to your labels, please do so now. Notice the importance of not only just the labels, but I also included the units of measurements and the titles of each graph. So feel free and pause, make sure everything's labeled appropriately. These questions for the synthesis are not in your workbook here, so I'm going to go ahead and ask that you just stop and think about these questions. And again, if you want to answer them at the bottom of page 5, there is space there where it would be a good place to take a look at these questions. And so why don't you go ahead and pause the video now and see if you can answer these questions, and then we'll go over them shortly. All right, the first one asks, what are some things you noticed about the numbers on the axes for the different scatter plots? Well, I don't know about you, but I noticed that not all of the axes started from 0, right? If I backtrack, take a look. So my first graph, yeah, the x-axis did, but the y-axis certainly didn't, right? It started from 6,000. My second graph, the x-axis started from 72 and the y started at 15. So neither of them started from 0. So that's kind of something new and unique that we've never seen before, that we're seeing with scatter plots here. So I'm going to add that to my notes. I noticed that all axes did not always start from 0. Something else that I noticed is that the units of measurements, the scaling in which they chose to go up by, wasn't something always like 1s or 5s or 10s or even 100s. Like if I backtrack, again, I look at the x-axis here and they're counting by 30,000s, right? Their y-axis, they're counting by 3,000s. So depending upon the needs of the data, these numbers vary, right? If I look at the second graph to go from 72 to 78, that's an increase of 6. So they're increasing each time by 6 units for their X data, and for their Y data, they are increasing by 5s. So the way that they're scaling is very unique to each situation. So I noticed that the scaling that they've chosen are all different, right? They're very unique depending upon the data we're analyzing. Why do you think it makes sense for the graph comparing temperature and energy to start at 72 and go to 102? So again, I'm going to backtrack to answer that question. So that's our second scatter plot here, the 30 days in August, to go from 72 to 102. So why did they pick those numbers? Well, if you look at the range of that data in the table, so go ahead to that 30 days in August and look at the lowest temp is around 77 degrees and the highest temp is 100, right? So they know that data has to fall between 77 and 100. So I'm thinking they chose a number slightly lower than 77 and something slightly larger than 100 to make sure all that data was encompassed here. So that was kind of their reasoning for choosing 72 to 100 as their scaling for their X data. Okay, so the range of this data falls between these numbers, more specifically the lowest of 77 and the highest of 100. So they picked numbers so that all those numbers would fall between like 72 and 102. Why do the numbers for the graph comparing temperature and energy go up by 6 rather than 1s or 10s? So going back to that same graph again, the second one, the 30 days in August one, they're again talking about this x-axis. Why are we counting by 6s? Why not 1s? Why not 10s? My thought here is if we count by 1s, the data might be too close together, right? And if we count, and there's just not enough lines, there's not enough space. And if we count by 10s, the data might be way too spread apart. So I think that was the reasoning, like, hey, let's pick something in between 1s and 10s. Why not 6s? Someone might have done 5s, which is still pretty reasonable. So if they counted by 1s, the data might be too close. If they counted by 10s, the data might be too far apart or spread out. Okay, so just some things to think about when scaling appropriately from data tables to scatter plots, right? All right, another set of questions that, again, unfortunately, is not in your workbook, but if you have some room and you want to jot these notes down at the bottom of page 5, good place to do it. How did you match the tables to the scatter plots? Well, we took a look at the scaling, right? The scaling was really important on the X and Y axes. And maybe we even attempted to plot a few points from each table to see, hey, where would this fall and how does it make sense? Why is it important to include labels on the axes and the scatter plots? So this is huge here. This is the first time we're seeing scatter plots or graphs not starting from 0. So since the data is jumping around differently and uniquely, and it doesn't always have to start from 0, it is super key and important to make sure that we include those units of measurement when we label our axes and be as detailed as possible. Why is it important to include units in label or in the axes of labels? So basically, I just kind of went over that that question. Again, more detail, the better, so we can relate the tables to the scatter plots. The same data is represented in the tables as in the scatter plots, which is easier to understand for you and explain your reasoning. So this is going to depend on you. Which visual model is easier for you to generate conclusions based on the data? For me personally, the scatter plots. I can see trends in the data a little bit nicer, a little bit easier. It's having that visual representation. So for me, the scatter plot works out really nice, especially when our data on the table is not ordered or sorted like that first activity when we resorted the tables to make more sense, to be more aligned with the scatter plots. Why would sorting the information in the table be helpful? So I basically just answered that question, right? So that your table can be read from top to bottom, that should correlate with your points being plotted from left to right, just a little easier to follow in both directions. When looking for relationships between two variables, what are some graphic representations that might be helpful to use? So we focused heavily on scatter plots here, right, for some graphic representations, but we know there's other graphic representations out there. An organized table, I guess we looked at both here. An organized table and scatter plots really helped us out. What is a scatter plot and how is it different from plotting points for a function? So a scatter plot, for your formalized definition, that you can go ahead and add to the bottom of page 6 there. Here is your formalized definition, so go ahead and press pause and copy this down at the bottom of page 6. Scatter plot shows data points for the relationship between two variables on a pair of coordinate axes, one for each variable. So there's our formalized definition, but to go back to that question, how is it different for plotting points on a function? So we know that functions, in order to be a function, each input has to have one unique output, so those outputs can't repeat. But that's not necessarily the case for a scatter plot. A scatter plot doesn't have to be a function because it's real data. It's collected from the real world. And we know not everything in the real world is going to be this perfect function that has a unique output. So that's the main difference between scatter plots. They don't have to be functions, and they can still be representing data. All right, let's go ahead and recap everything in your lesson summary on page 6. So you've got 2 different sets of tables. Yours are organized from left to right on your paper. Mine are top and bottom. But we have the unorganized data in the first set, the first table. And you can see when the data is unorganized, it's really difficult to find a pattern. It's just kind of random, right? Everything's all over the place. If we're talking about a toy car and I pull back the string, if I pull back 6 inches, the distance the car travels is 23.57. So that's how this table is read. If I pull back 1 inch, the distance it travels is 8.95 inches. But now if I reorder this table from distances pulled back in inches from smallest to largest, like the second one in your workbook or the second one here on my slide, I can see more of an association with the data, right? If I pull back 1 inch, my car is going to travel approximately 8.95 inches. If I pull back 2, my car is going to travel 13.86. If I pull back 4 inches, my car is going to travel 18.48. So as we can see, when the data is reorganized, the further I pull back the string, the further the car is going to travel, right? So reorganizing that data clearly helps us see that. We can further see that visually by making a scatter plot. And this scatter plot, sorry, let me get rid of that. This scatter plot, unfortunately, is not in your, oh, it is. I'm sorry, it is in your workbook on page 6. So we can use it to answer the question, how far will the car travel? How can we estimate how far it will travel if we pull back the string 5 inches? So that's where I'm going to go ahead and look for that 5 inches and go up, 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 up. And this may be a good place where that would fall, a point that would fall in line with the majority of the data. So we can answer that question. And that's approximately, we can expect the car to travel approximately 20 inches, right? All right. So patterns in data can sometimes become more obvious when recognized in a table or when represented in a scatter plots or other diagrams. If a pattern is observed, it can sometimes be used to make predictions, which is what we just did right here. If I pull back 5 inches, I can expect the car to travel a distance of approximately 20 inches. And again, these are approximations. You should have that in your notes at the bottom of page 6 at this point. And when all of your notes are solidified, you can go ahead and get started on the 6.1 cool down, squashed spheres. As soon as you're done filling out this cool down, please turn it into the inbox. And should you finish everything early, you can go back and try the Are You Ready for More? And then work on the practice problems on pages 7 and 8 in your workbooks.